Welcome back. In this part of this lecture series, I will be trying to find out the electric field due to dipole at an arbitrarily far off point. That means we are considering the distance of that point of observation from the center of the dipole quite large in comparison to the length of the dipole. Let's find out electric field due to this dipole. Let's say minus q plus q, that is the dipole, and it has got total length 2l, l and l, and the point is neither on the equatorial line nor on the axial line. Let's say it is somewhere over here. To join these points, the center of the dipole with the point of observation, this distance is say x, and we are assuming, although not pictorially shown like that, but we are assuming that x is quite large in comparison to L. This is L, this is L, let's say this angle is theta. So dipole moment is in this direction. Let me draw it. Let's say the dipole moment, I draw it with the help of this broad arrow, let's say, and this is dipole moment, minus q to plus q, p. What I can do, I can resolve this p into its rectangular components. I can resolve this p, the dipole moment, into its rectangular components like this. What do we have? We get two vectors, two rectangular components, one in this direction, the other in this direction, the two rectangular components of p. Now, if this angle is theta, you can without any problem assume this angle to be theta, no problem at all. If this angle is theta, this becomes p cos theta and this becomes p sin theta. Now, instead of finding out electric field due to this dipole moment p, what we are trying to do is we'll find out electric field due to this dipole having dipole moment p cos theta, and we'll then find out the electric field due to this dipole having dipole moment p sin theta. For p cos theta, the point of observation, say capital P, lies on the axial line. So electric field due to a dipole on its axial line has the same direction as that of the dipole moment. That means if p cos theta is acting in this direction, the electric field due to, let's say I call that E1, would be in the same direction. Whereas for this dipole having dipole moment p sin theta, the point of observation capital B lies on the equatorial line, and from the previous lecture we already know that on the equatorial line the direction of electric field is opposite to dipole moment. So if dipole moment is acting in this direction, the electric field, let's say I call that E2, it would be acting in this direction. And then once we find out E1 and E2, it would be easy to complete the parallelogram and obtain the total electric field E. So let's proceed with, first of all, let's find out E1. We know that E1 is the electric field due to a dipole having dipole moment p cos theta at a point on its axial line. I repeat, we know that E1 is the electric field due to a dipole having dipole moment p cos theta at a point lying on its axial line, and that too at a far off point. So we use the expression which we derived in the previous part of this lecture series, that is 1 by 4 pi epsilon naught 2p divided by x cube. This was the expression when the dipole moment was p, but in this case the dipole moment is p cos theta, so I modify this expression as 1 by 4 pi epsilon naught 2p cos theta divided by x cube. Similarly, what about E2? Now E2 is the electric field due to a dipole having dipole moment p sin theta at a point which is lying on its equatorial axis, and that too at a far off point. Under this condition, I repeat, E2 is the electric field due to a dipole having dipole moment p sin theta at a far off point on its equatorial axis. From the previous part of this lecture series, I know E2 is 1 by 4 pi epsilon naught p by x cube. But when we derive this expression, the dipole moment was P. In this case, the dipole moment is P sin theta. So I modify this relation as P sin theta. Once I know E1 and E2 acting at mutually perpendicular direction, yes, because I have taken these components as rectangular components, and one of the vector E1 is along that one vector and the other is along the other vectors. So E1 and E2 are also perpendicular to each other. So need not to tell you that resultant would be E1 square plus E2 square plus 2E1 E2 cos 90 under the root. The term containing cos 90 get vanished because cos 90 is 0. And what is the expression for this? Once I'll have to square this out and take this sum and then take the square root. I can see that there are few things which can be taken out common, like 1 by 4 pi epsilon naught x cube and p. I think these part of the expressions are common in both the terms. So one to remain inside the square root, there is 2 cos theta square. That means 4 cos square theta plus sin theta square, that is sin square theta. And what I can do, I can write it down as 3 cos square theta plus cos square theta, that will become 4 cos square theta. No problems with that. I can write down 4 cos square theta as 3 cos square theta plus cos square theta, and there is one more sin square theta. So it becomes 3 cos square theta plus cos square theta plus sin square theta, which is 1. So this is the final expression for electric field due to a dipole at a far off point, at a far off arbitrary point. How can you change this expression to special case of equatorial line and axial line? If this point lies on equatorial line, just make theta equal to 90 degrees. And if it lies on axial line, just make theta equal to 0 degrees. You will derive again the same expressions. If theta is 90, it will be this term will vanish. It will become p by x cube. And if theta is 0, it will become 2p by x cube. What if in a question this angle is given to be theta? No problem. In your expression, change theta to 90 minus theta. So it will become 3 sin square theta plus 1. I hope you are very much capable of doing these. You can play with it basically. Now there are 2 more articles which I want to deal with in this part, and then there are very beautiful inferences drawn from those expressions. So let's proceed with that. The next part which I am going to deal with is electric field due to the torque on a dipole when placed in uniform external field. Torque on a dipole placed in external uniform field. Let's say some external source is producing uniform electric field E, and in this electric field some dipole is placed at an angle with its dipole moment inclined at an angle theta with the direction of the electric field. This is, I am assuming, minus q, this is plus q. Dipole moment is acting from negative to positive charge, and electric field is acting in this direction. The angle between the dipole moment and the electric field I am assuming to be theta at this instantaneous position. Now what happens? The plus q charges, they always tend to move along the electric field, so it experiences a force in this direction which is given as q times c. If you remember, electric field was nothing but force per unit charge. So what is the force? Force is cross multiplication of force is by cross multiplying q into e. The negative charge will experience the same force because the field is same and the charge is also same. But since it is negative, it will experience a force in the opposite direction. That is equal to QE towards me. Two equal and opposite forces with different line of action. What do? They constitute a couple which exerts a torque. It is interesting to know that only when two forces are equal and opposite, but they have different line of action, only then they can rotate something. For example, consider this pen. If I push this pen in upward direction and pull it downward, that means one force is acting along this line, the other force is acting along this line. What will happen? It will get rotated. But what if I apply the force along the same line? If the line of action of two forces is same, the forces will simply cancel out each other, and in this case no torque will be exerted. So the primary point of consideration in this diagram is that the two forces are having different line of action. Think of a situation where they will have same line of action. That means when they will be cancelling out each other. Do you know what those positions will be and how many such positions will be there as the dipole rotates? We'll get the answer in few minutes. First of all, let's find out the expression for torque. There is one force QE acting in this direction, the other force is acting QE in the opposite direction. They are equal in magnitude, they have got different line of action. The torque exerted is given as, the expression for torque is either force into perpendicular distance between line of action of two forces. Torque is given as the product of either force, because both of them are equal, so I can take either force and product of either force and the perpendicular distance between the lines of action of two forces. So what is that perpendicular distance? It's very easy. Just extend these lines. This is the line of action of one force. Extend this line. This is the line of action of the other force. So the perpendicular distance is this much. Let's say I call that x. This distance is 2l. This angle is theta. It is very easy to say that x by 2l is equal to sine theta. So perpendicular distance is 2l sine theta. Just putting over here, torque is equal to either force, which was Q into E, into the perpendicular distance which you formed out, 2l sine theta. Q into 2l can be written as P. So it is PE sine theta as far as its magnitude is concerned. In vector form, torque can be written as P cross E. Torque can be written as P cross E. There are very interesting two special cases which need to be discussed. For example, what if theta is equal to 0 degrees? We know that sine 0 is 0, so torque is 0. What if theta is equal to 180 degrees? Again, sine 180 is also 0, so torque is again 0. In both the cases, the system is in rotational equilibrium. In both the cases, the system is in rotational equilibrium because the torque acting on the dipole in both cases is 0. But are these two equilibria identical in nature? The equilibrium when theta was 0 and the equilibrium when theta is 180 degree, are these two equilibria identical? We don't know yet. Let's find out one more thing. First, let's elaborate these things. Theta equal to 0 means this was like this. Dipole, let me draw two more diagrams. Consider this case. Minus q over here, plus q over here. Dipole moment P is in this direction. Electric field E is also in the same direction. The angle is 0 between P and E. Torque is 0 because the perpendicular distance between the lines of action of two forces is 0. This q wants to go in this direction, this minus q wants to go in this direction. Both of them are pulling the dipole in opposite direction along the same line of action. That was the case when I was pushing this pen like this from upward and downward direction together along the same line of action. It simply cannot rotate in this situation. So theta is equal to 0. This is this equilibrium. And there is another equilibrium. Let's say I flip over the whole of the dipole such that plus q is over here, minus q is over here, A is in this direction, dipole moment is in this direction. What is the angle between P and E? They are opposite, 180 degrees. Theta is 180 degrees. Still, now minus q wish to go opposite to electric field, plus q wishes to go along the electric field. They have got again same line of action. Again torque is 0. But are these two cases identical? Are the two equilibria identical? To understand this thing, we'll go to the next topic. Let's find out the potential energy of the dipole when placed in external electric field. Potential energy of a dipole when placed in external electric field. So we have got electric field, uniform electric field produced by some external source, and we have got a dipole placed like that. Let's say initially it was at some angle theta 1 and I rotated it through small angle d theta. I had to do small work. This is minus q, this is plus q. I had to do some small work which is given as torque into d theta, as in translatory linear motion. Translatory linear motion, what do we have? Force into displacement. That gives us the work done. In case of rotational motion, it is torque into angular displacement, which gives us the work done. dW is the work done. Expression for torque we already know, which is PE sine theta. Then we get d theta. How can we find out the total potential energy of the system? Total potential energy stored in the system is basically the work you have done in rotating that dipole through some angle from theta 1 to theta 2. So potential energy total can be calculated by integrating the above expression, that is PE sine theta d theta, in the range from theta 1 to theta 2. So what is potential energy of the system? Potential energy of the system is PE is constant. It comes out of the integration. The integration of sine theta is minus cos theta from theta 1 to theta 2, which turns out to be minus PE cos theta 2 minus cos theta 1. So this is the expression for potential energy. We can simplify this thing by assuming that initially it was at right angle to the electric field. That means, let's say theta 1 is 90 degrees and I rotated it through an angle theta, so theta 2 is theta. So potential energy of the system can be written as minus PE cos theta. Potential energy of a dipole rotated through an angle theta is given as minus PE cos theta when initial angle theta 1 is taken to be 90 degrees to the electric field. Now let's explore the same two cases of theta equal to 0 and theta equal to 180 degree to see what is difference in the two cases. When theta is equal to 0 degree, what is the potential energy of the dipole? Look at it. When theta is equal to 0, cos 0 is 1, what is the potential energy? Minus PE cos of 0, which is minus PE cos 0 is 1. So potential energy is minus PE for theta equal to 0. But for theta equal to 180 degrees we get. For theta equal to 180 degrees, potential energy is equal to minus PE cos of 180 degrees. Cos 180 degrees is minus 1, so it turns out to be plus PE. In both the cases, the torque being exerted on the dipole was 0. In both the cases, the dipole was in rotational equilibrium, whereas their potential energies are not same. This has got a potential energy minus PE, it has got energy plus PE. That means that when the angle of the dipole with the external electric field is 0 degree, it is at lower energy, and when the angle with the electric field is 180 degree, it is relatively at higher energy. This type of equilibrium, when energy is minimum, although equilibrium is there, but energy is minimum, is termed as stable equilibrium. Whereas when theta is 180 degree, equilibrium was still there, but the energy is not minimum, rather it was maximum in this case. So this is called an unstable equilibrium. You can very well understand this case by this analogy. Consider a small marble placed on or inside a bowl. Consider a marble inside a bowl or on top of a bowl. You can keep it stationary over here, but once you disturb it, will it go back to its original state? No. It will remain equilibrium as long as it is just at the top. You just displace it from its equilibrium position. It will not go back to its equilibrium position because it is at the highest energy, and system always tries to go to the state of lowest energy. This type of equilibrium is called unstable equilibrium, which is referring to case of 180 degrees of the dipole. Whereas in this case, the equilibrium is there, but energy of the system is also minimum. Even if you disturb it slightly, you take this marble to this position and release it, it will still come back after oscillation. It always tries to come back to its mean position again, that equilibrium position again. This equilibrium is stable equilibrium. This is referring to a case of theta equal to, and obviously sometimes like this is called neutral equilibrium, but that was not the case over here. So this is stable equilibrium corresponding to theta equal to 0. This refers to unstable equilibrium of theta equal to 180 degree. This means that if you displace a dipole through small angle, this is minus q, this is plus q, this angle theta is small, you have just disturbed it, theta let's say 5 degrees. You disturbed it and then you released it. What happens? The system will start oscillating about. The system will start oscillating about its mean position, and if some damping is there, ultimately it will again settle back to its same state. If there is no damping, it will go on oscillating for infinite time, but if there is damping, it will come back to its mean position, like this. If you disturb the dipole, it will oscillate and finally settle down again parallel to the electric field. But what? This is theta, the equilibrium case, theta equal to 0, disturbed through small angle 5 degrees. What if you have got dipole at 180 degrees and you disturb it through 5 degrees from 180 degrees? That means this plus q is over here, minus q is over here. Now this is not the case of minimum energy. What will happen? It will just flip over again. The moment you disturb it from its equilibrium, unstable equilibrium position, it will not come back to that state, rather it will completely flip over and try to go to the state of minimum energy, which is also the state of stable equilibrium. This is very, very important to understand these concepts, and